So this is Electrotech 1303 experiment 4. You'll notice I have the DC machine here set up as in step 2 for field speed control. I have the DC milliamp meter connected in the shunt field circuit. I have it connected to terminals 8 and in on the power supply, fixed 120 volts DC. In the simulation, if the power supply breaker trips, you should switch to terminal 7 and in. Put the voltmeter selector switch in 7 and in. You notice there's an 8 and in here. The voltmeter will then read terminal 7 in. Use this control knob to turn it up so that it's at 120 volts. And the reason why you might have to do that, you notice that 8 and in here is rated for only 2 amps. With a load on the motor, it will probably draw more than that. You know, I'll normally use 8 and in when we're in the lab. The idea is that until we put a load on it, 8 and in is good. Perhaps in the later stages, I think steps 5 to 8, you might need to switch to 7 and in. We'll see. Now, so if I turn on the power supply, the motor starts immediately, and you'll notice now there's a field current. As we adjust the field rheostat, you'll notice that that current will change and the motor speed changes as well. And so I can go up to more than 400 milliamps or 0.4 amps, and so then there's the minimum current that's here as well. And notice that minimum current is about, 160 milliamps for this one, and the slowest speed is obtained there. And so I'm not going to take measurements in this section. What I want you to do is get the measurement from the simulation. And so you'll notice as well, the dynamometer is running here, and I have the belt on. But it's not necessary to put the belt on to complete this section. The lab doesn't actually ask you to put the belt on, so whether you put it on or not is immaterial for this particular part. Now I have the motor connected for armature speed control according to figure 4.3, and you'll notice we're using both power supplies now. I have the selector switch this time placed on 7 and in, so that when I turn the power supply on, nothing happens to the motor as the voltage across the armature is at 0. I also have this voltmeter connected across the armature, so when I increase the armature applied voltage, you'll notice the motor speeds up accordingly, and I can put that armature applied voltage up to the rated value of 120 volts. If I do that, I'm attaining the maximum speed. I have just a set voltage on the shunt field, so the shunt is not adjustable on this, but the armature applied voltage is adjustable, of course. And as I turn that down again, it will slow down. For this part as well, I want you to get your results from the simulation, so I haven't taken any results here. So now we're set up as according to figure 4-5 for steps 5 through 8. And you'll notice that we are indeed using 7 and in on the power supply, as it has the higher current rating, 8 amps. And so both the milliamp meter and ammeter that's in the circuit. The ammeter measures IA, the milliamp meter measures IF. The sum of those two will give you the line current that enters the motor. Remember, power in is the line current multiplied by the source voltage, which you will have set for 120. Okay, so the field circuit now is in there, so the rheostat is in for speed control if we need it, and we will have to adjust the speed starting off in the first step. In this one, here's our dynamometer. I have the dynamometer connected to terminals 1 and in, as it's rated to run off 120 volts AC. Now you might find that in the simulation the dynamometer is quite a bit different, and so it probably has its own internal power supply, as it's a dynamometer power and a power supply and a prime mover as well. And so the electrodynamometer is what we use as a load for the motor. And you know, in the lab here, we can't bring in a practical load, so the dynamometer is a simulated load. And our dynamometer is a bit different, like I said, from the one in the simulation. They got two dynamometers in there. One of them is a 4-quadrant power supply on a dynamometer. That's not the one we want to use. We want to use the dynamometer prime mover. And that one, like I said, I believe it has its own power supply. And you can set it up to be a load. And you can set it up to show the load in inch-pounds of force, or I guess Newton meters for that one. Or you can show the speed that it's rotating at. Now, normally, the dynamometer we use in the lab has imperial ratings, the torque 0 to 27 inch-pounds of force. And on the scale inside, you measures that in, like I said, inch-pounds of force. So if I pop the door open, you can see the scale down here. And as the dynamometer spins, we're inch-pounds of force in there. Now, the dynamometer in the simulation, I assume, has metric units, which means that instead of using the table in the lab, which has imperial units, and the graph, figure 4.6, which also has imperial units in inch-pounds of force, you're going to have to switch the torque here to Newton meters, 0.3, 0.6, 0.9, and 1.2, and they're not equivalent to these values. And you'll also have to change the scale on your graph slightly. I will put the tables with the new units and values to use in the supporting document. Okay, so now if we turn the dynamometer down to minimum load, we will turn the power supply on, and step asks us to measure the voltage and the field current where we have attained a no load speed of 2000 RPMs. And so what that means basically is turn the voltage up until you get to 120 volts. The motor is running, and now you can take the speed, and it's more than 2000 RPMs, so that means adjust your field current to slow it down a bit until you get to 2000. Okay, so that's about 2000, and a little bit high, and so I can slow it down some more. I'm at 2. Okay, so I'm closer to 2000. I'll slow it down another bit. I don't have to be exact. And so now that I have right around 2000 there, and look again, I can slow it down a bit. Seems like it. Okay, so now I can take that milliamp reading as 200, and my IA, which I don't need right now, is just over half an amp, and my applied voltage, which should be 120, which it is there right on the money. And so that's my measurements for page 6 in step 6 and 7. And now it asks me, don't change the field rheostat for the remainder of this part of the experiment. Okay, so all we're going to do now is we're going to change the load on the dynamometer. And so you need 2 hands to do this, because you got to keep this lever here over while I turn this button. And so the idea is that as I turn it up, the percent load here, I can read the load on the motor and the little red line in there. And then once I have 3 inch-pounds of force, or 0.3 Newton meters in the case of the simulation, then I can measure the speed and record that in the second line of the table. Okay, and the speed in the first line should be about 2000, or in my case here I got 2049. But you should be able to adjust it really close to 2000 in the simulation. And once you fill up the table, then you will do the torque speed graph. Remember that because this is a shunt motor and we have adjusted it and we're going to keep the field current constant. A constant field current means that, yes, the torque speed curve should be really close to linear. Now, I'm not sure that you can do step 11 in the simulation, and so I'm going to make a measurement for that here. And so we have, after step 8, returned our voltage control knob back to 0. We still have this on 7 and in. And as per step 11, we have increased the control knob on the dynamometer to 100%. So that gives the motor a full starting load. Now, when I turn the power supply on, the motor won't move because its armature voltage is at 0. And as long as we don't increase the rated current of the armature winding, which is at 3 amps, and you can see it there, right? Then we won't damage the motor. Now, the motor has a full load on it, but we're going to increase the current here until we goes to 3 amps. And again, we will have a low voltage, but 3 amps. Okay, so 3 amps. Now, you'll notice the motor should be turning slowly or not at all. Well, it's not moving. Okay, and the voltage that we have is this one. And I would say that that voltage is 28 volts, maybe. Okay, so again, dynamometer, I normally expect it to be turning kind of slowly. It asks us for a measurement on torque. And so, you know, if you're going to make that measurement, there's not much, you know, I got less than 1.2, let's say. And so that's pretty low. Careful, now, I get fingers in there and that's on, right? Okay, so the voltage is the most important measurement there. And like we said then, you know, it's looking like almost a bit less than 30, right? So 28 or 29 probably. Okay, so with that voltage then, you should be able to remember that because the armature is not moving, there's no induced voltage E0. If you think about your armature loop now, the only resistance in it is RA, and the only voltage is your applied voltage. And so you got 3 amps, you got your applied voltage, that gives you a measurement of RA. And this is a measurement of RA under experimentation, right? And so we already measured RA in Lab 2, and this is another measurement for RA, slightly different. In step 12, they asked you to go ahead now and calculate the lock rotor current, assuming that the voltage was all the way up to 120, but we have only a 28 or 29 or something like that. And so if you had the armature resistance you just calculated, but you had 120 volts, what would the resulting starting current be is what step 12 is asking you to do. Okay, so that's the end of the lab, 13.5 minutes.